we're going to take a look at the second part of 3.1. So we're talking about inverse trig. And remember that inverse trig is used to undo regular trig. All right, so just as an example, take this. And actually, let's just take this one. So we took the sine, inverse sine of 1/8, and we got 7.18. Okay. So if we wanted to get the original answer back, we could use regular sine. Okay, let's do another one. Let's take the regular sine of 20 degrees. And you get 0.34202. Now, let's take the inverse sine of 0.34202. So inverse sine of 0.34202. It's not exact, but when I hit enter, what do you think I'm going to get pretty close to? 20. Right, in this case, we get 19.99999. It's because I rounded it. Right, so basically, if you do this, we took the sine of 20, and then we took the inverse sine of what we got when we did the sine of 20. So we took the sine of 20, took that number, and then took the inverse sine of it. And when we did that, we got back exactly the same number we started with. And that's because what happens is these two things cancel each other out. It's kind of like if you wrote, 3 squared square root. Well, you just wrote down two things that are going to cancel each other out. Squaring and square rooting gives you back the original thing you started with. Taking the sine of the inverse sine gives you back the original thing you started with. So any question on that idea? So without actually typing it in two steps, let's do it all at once. Let's take the inverse sine of the sine of 78. When I hit enter there, what should I get exactly this time?
78.
Yeah, I get 78. So I got exactly back the same thing I started with. And the reason I got the exact answer this time is because I didn't round it. I just typed it all in one step. So here's basically the general formula for what we were just doing, but not putting in a specific number. If you take the sine of a number, and then take the inverse sine of what you just did, you're going to get back the same thing you started with. Just like here, I got back to 78. Now, does anyone remember yesterday what we said about inverse sine? It always gave you a number between two values. Yep?
-90 and +90.
Right. So when you take the inverse sine of this, because you're doing inverse sine, it's going to force this to be between -90 and 90, always. So what happens if you put a number in here originally that wasn't between -90 and 90? Well, you're not going to get that number back. So I picked a number like 78. That's between -90 and 90. Well, let's do another one. Let's do -23. So let's do the inverse sine of the sine of -23. Is -23 between -90 and 90? Okay, no?
Yeah.
Yeah. So it works fine. Let's try the inverse sine of the sine of 120. So now, if you just plug in a number that's not between -90 and 90, but inverse sine is going to force this answer to be between -90 and 90. So what happened that time is, it couldn't give us back the same answer, because it has to always give you an answer between -90 and 90. So these two things do cancel each other out, and you get back what you started with, as long as you start with something between -90 and 90. This formula doesn't work if you pick a number that's not between -90 and 90. So -90 and 90 in degrees, And in radians, that's negative pi over 2 to positive pi over 2. And we're going to look at two versions of each formula. Okay, version A is going to have the inverse on the outside. Version B is going to have the inverse on the inside. And the difference is just order of operations. Which one are you going to do first? And if you, let's just pick an example. If you type in something like sine of inverse sine, so typing it in just like we see the pattern here, sine first, then inverse sine. And let's do 0.28. When I hit enter, I got back the same thing I typed in. So what happens? Sine and inverse sine cancel each other out, just like squaring and square rooting. But there's a restriction here. It can only cancel itself out if the original number you typed in was between -1 and 1. If you try a number that's not between -1 and 1, okay, when we tried it in the formula above, you pick a number that's not between -90 and 90, and you hit enter, you just get a different answer back than what you started with. The example I showed you guys was 120. Well, let's try it here. Let's do the sine of the inverse sine, and let's pick a number that's not between -1 and 1. Let's do 2. So last time we got a number that was just different than what we started with. This time you don't even get an answer back. Okay, you can't even do it. And the reason why it doesn't work, and we're going to talk a little bit more about this next week, is because I want you to take a look at that graph. Okay, that's a picture of the sine graph. Okay, sine it's not a straight line when you draw it, it's a wave. And if you look at the wave, can anybody see the highest that it looks like the wave ever goes? Yep. 1. And how about the lowest? Yep. -1. So the fact that the graph of sine goes as high as 1 and as low as -1 is exactly where these two numbers are coming from. Okay, we haven't studied too much about the graphs, but that's where it's coming from. And by plugging 2 in for x, what you basically tried to do was this. You put a line at 2. Where does that black line cross that red wave? You want to see where it crosses?
It doesn't.
It doesn't. It never will. So you're basically asking the question you can't solve when you plug in a 2. If you plug in a 1 or a -1 or any other number, then you can find where it crosses the red wave. And you notice it crosses a lot of times, right? If you put a line in, like that's maybe about 0.5. So you get lots of answers. Well, how would you know which one of these answers to write down? That's what we did yesterday. You always write down the one between -90 and 90. So in this case, that's the one you'd write down. All right, so this is just kind of visually showing you what we did yesterday. We talked about multiple answers. There's a picture of how you get multiple answers. And you always pick the one that's between two numbers. All right, let me just move that off. So, kind of question you could see on something like this. This is basically a yes or a no. It's saying if you take the inverse sine of the sine of pi over 8, will you get pi over 8? Okay, so first thing we want to do is see, is this more like formula 2a or 2b? Which pattern does this one match up with? Yeah? This is A, because the inverse is on the outside. All right, so we're plugging in pi over 8, and there's no degree symbol, so we know we're dealing in radians. That means you're looking at these two numbers. So we have to figure out if pi divided by 8 is between negative pi over 2 and pi over 2. Now, when we have to figure it out with the pi, a lot of people have trouble because of the fraction. So, first of all, what kind of number is pi over 8? Is it a positive number or a negative number? It's a positive number. So, think of negative pi over 2 to pi over 2 as a number line. Pretend like negative pi over 2 is here. Positive pi over 2 is exactly the same distance away on the other side. Well, we know pi over 8 is positive. So the question is pi over 8 somewhere in there? It's not going to be here. That would be negative. Okay, so we want to see it. Is it in that section? If you take pi and divide it by 8, how does that compare to pi divided by 2?
Smaller.
It's smaller. Right? If you take something and divide it by 8, it's smaller than when you divide it by 2. So it's smaller than pi over 2, but it's still positive. So would it be in the red section?
Yes.
Yes. Okay. Smaller than pi over 2 means it's to the left of it, but we know it's to the right of 0 because it's still a positive number. So maybe it's somewhere, like in there. So the answer there is yes. That will work because pi over 8 is between what it had to be. Let's try another one. Inverse sine of 3 pi over 2. If you were to do that out, would you get 3 pi over 2? So, inverse is on the outside. So we're still checking if we're between negative pi over 2 and pi over 2. All right. 3 pi divided by 2. Justice, what kind of number would that be? Positive or a negative?
Positive.
Positive. So I'm just trying to help you break it down and think about it step by step. So it's a positive number. So the question is 3 pi over 2 in that section? It's not going to be here because those are negatives. Right? We know it's positive. How does 3 pi over 2 compare to pi over 2?
It's greater.
It's greater than pi over 2. Right? 3 pi over 2 is triple pi over 2. So 3 pi over 2 is way over here. Is it going to be in that red section? No. 3 pi over 2 is too big. It goes over the upper limit that you're supposed to use by 3 times as much. So the answer here is no. This is the type of problem, if you type it in, you wouldn't get an error. It's the first type. You'd get a number back, but it just wouldn't be the one you started with. All right, let's try this one. So, it's saying, is the sine of the inverse sine of 1.5 going to equal 1.5? What's different about this one compared to the first two? Justice?
It's in decimal form.
Okay, so yep, the argument, it's a decimal. What else is different about maybe the setup of the equation? Yep, Gina?
Formula B said.
Formula B. The inverse is now on the inside. Formula B says you're supposed to be between negative 1 and 1. Is the number that we are trying to plug in between negative 1 and 1? No. So this is the example where you're kind of putting a horizontal line and seeing where it crosses. The graph never goes this high. It stops at 1. So the answer here is no. That would not work. All right. Bless you.
Thank you.
Hey, how about this one? The sine of the inverse sine of 0.6. Would that equal 0.6? Think about what formula it is, and then look up what numbers you're supposed to be between, and then ask yourself if that number is between them.
Yes.
Yes, because what are you supposed to be between?
Negative 1 and 1.
And the inverse is on the inside. This formula works if you're between negative 1 and 1. So the answer there, yes. Now, another way you could see a question like this written, instead of a yes, no, you could have something like this. It could say simplify, and it would say the sine of the inverse sine of 0.6. If I word the question like this on the test, simplify, don't write yes. That doesn't answer the question. So simplify means do this out and tell me what the answer would be. So based on what we just did up above, you should know the answer. What's the sine of the inverse sine of 0.6? 0.6.
On the test, is it fair to say like when to simplify and when to say it's no?
So if it would either be worded is, if it says is something true, then the answer is yes or no. And then if it says, it would say simplify as a separate direction.
Okay.
So, yeah, it'll be worded clearly. Yeah. Questions on that? Okay, so each trig function we're going to look at has a formula A and a formula B, okay, for when it works. So let's look at this one. Inverse cosine of cosine. Those two things cancel each other out. Just to be clear, these parentheses have nothing to do with multiplication. It's just two functions next to each other, just like this. That doesn't mean to do anything with multiplication, just because you have a symbol right next to a number. It just means take this number and plug it into that symbol. That's all. There's no multiplication. Okay, so think about when we talked about inverse cosine yesterday. What did we say inverse cosine always had to be between? So the inverse sine is negative 90 to 90. Yep.
0 to 180.
0 to 180. So the A version of every formula we study today will always work if you're between the numbers we talked about yesterday. The B version of the formula has to do with a picture of the graph and how high and low it goes. All right. So if you put in, say, 120, that would work fine. Don't look at it quick and say, oh, it's bigger than 90. It doesn't work. It's okay if you're bigger than 90 this time because you're doing cosine. All right. Now, the B version. That's when we switch the cosine and the inverse cosine. The B version has to do with how high and low the graph goes. So let me graph. We haven't seen what cosine looks like. I'm going to graph cosine in blue, right next to sine. So cosine is being drawn in blue. How high and low does it look like that one goes? Yep.
The same as sine.
It's the same as sine. If you notice, it's what we call a horizontal shift. So it's a little, cosine is a little bit to the left, but it still goes up and down the same amount. And that's where this negative 1 and 1 is coming from. All right, let's try a couple examples here. All right, so first one is the cosine of the inverse cosine of 0.95. Would that come out to 0.95? So Tyler, which formula is this? Is this the 4a or the 4b? 4b. Yeah, inverse is on the inside, so it's the 4b. And what are we supposed to be between for what we plug in?
Between negative 1 and 1.
And did I plug in a number between negative 1 and 1?
Yeah.
Yep. So that's going to work. It's getting close to 1, but that's okay. That'll still work. So the answer there would be yes. And let's try this one. The inverse cosine of the cosine of 210. So look at where the inverse is. Look at if it's on the inside or the outside. Match that up with the formula up above. and see what you're supposed to be between. Okay, would this one work? Okay. No. Okay, that wouldn't work because we are plugging in a number that's bigger than 180. That's as big as you can go and have this formula work. You wouldn't get an error if you typed it in. You just get a different answer back. All right, so the answer there is no. Questions on those two? All right, and then the last thing for 3.1. The tangent lines. Okay, so if you take the inverse tangent of something you already took the tangent of, it will give you back what you started with originally if you started with something between. What two numbers do you think we have to be between, Jason?
Between negative 90 and 90.
Yep. So inverse tangent will undo regular tangent as long as you started with a number between negative 90 and 90. Or radians, negative pi over 2 to pi over 2. Now, when you switch it and look at it the other way around, the restriction on the variable here is always how high and low the graph goes. Sine and cosine both were between 1 and negative 1. Well, let's look at tangent. I'll just do tangent in green. Draw that. How high and low does it look like tangent goes? Yeah, it's going to go forever. It doesn't just stop, like the top of my screen is 4. It doesn't stop at 4. If you zoom out, it just keeps going. In this class, we don't really talk a lot about the graph of tangent, but I just wanted to show you that it does go up and down forever, which means this formula always works. There is no restriction on when it would or would not work. It always works. So if you see inverse tangent on the inside, you don't even have to think about it. Always works. All right, let's try one of those. If I did the tangent of the inverse tangent of 30.4, would I get 30.4? Allie?
Yes.
Yes, because 30.4 is definitely between negative infinity and infinity. It's definitely going to work. All right, so the first page, the homework, it's going to have, I think, 8 or 9 questions just like that, and they're all yes or no. Questions on 3.1. Good. So, last section, 4.1. So we'll do part of 4.1 today, and then we'll finish the rest of it tomorrow. All right, right triangle trig. So, goal in this section, by the time we're done it, is for me to be able to give you a triangle, and you can tell me how big all the sides are and how big all the angles are. You might have done a little bit of that in geometry or algebra 2. Things were thrown off the past couple of years, so if you don't think you ever did that, that's fine. So first, the title of the section is Right Triangle Trig. So let's just review what that word means. What makes a triangle a right triangle? Ethan?
It has a 90-degree angle.
It has a 90-degree angle. Okay, so that's a triangle with a 90-degree angle, and the symbol we usually use for that is a little box, little square in the corner that's a 90. What else? So if we have a right triangle, there's a name for the side that's across from the 90. It's always the longest side. Yeah.
Hypotenuse.
Hypotenuse. And then there's also a name for the two short sides. Anybody know what you call the Shorter sides, Ethan?
The opposite and adjacent.
So we're going to talk about those two terms in a little bit. Yes, they're called opposite and adjacent, and there's also another name that describes both of them. It's a little bit more generic.
Is it legs?
The legs, yep. One of these legs is opposite, one of them is adjacent. In this picture, you cannot tell which one is which because something's missing to figure that out. We'll talk about that. All right, and these, I'll just mark them. Those two angles that I just checked off, those are both what we call acute angles. What makes an angle acute? Yep.
Less than 90 degrees.
Yep, it's less than 90. Now it still has to be greater than 0. We've talked about negative angles a little bit. So like if I said to you it's negative 200 degrees acute, no. It's less than 90, but it's not greater than 0. And when you're talking specifically about a triangle, negative angles don't even make sense, so those wouldn't come up. There is a theorem that you can use in right triangles, in fact only in a right triangle, and it helps you to figure out the sides. Does anybody know the name of that theorem, Emma? Yep, the Pythagorean theorem. And can you tell me how you remember the formula for that?
A squared plus b squared equals c squared.
All right, so a squared plus b squared equals c squared. Now, I don't have an a, b, c anywhere in my triangle. So can you tell me what does a represent?
Leg 1,
Yep, and what about b?
leg 2,
And c?
hypotenuse.
Yeah, and what about each one of those?
They're the square values.
So when you say leg, like a is leg 1, what is it about leg 1? It's
The length.
the length, yeah. So A, B, and C are all lengths. A and B are the lengths of the legs, and C is the length of my hypotenuse. So that's a theorem that you can use to figure out sides. This has nothing to do with angles at all. If you want to figure out an angle, that's what we talked about yesterday. Inverse trig. Inverse trig is how you figure out an angle. And that's what we're going to use inverse trig for tomorrow, finding an angle. All right, so what we're going to do in a second is I'm going to give you the definition of all 6 trig functions. Now, we've done that before, sine, cosine, tangent, cosecant, secant, and cotangent. And the way we did it last week was on a unit circle. Sine was y, cosine was x, tangent was y over x. And then we had to flip those to get the other 3. Well, this week, we're not going to be describing it in terms of a coordinate. We're going to describe it in terms of 3 words. We're going to use the words opposite, adjacent, and hypotenuse. Well, so the first thing, I think everyone understands pretty good what hypotenuse is. That's the side that's always across from the 90. But opposite and adjacent can be a little tricky, so let's talk about what those are. So here's a triangle. First of all, opposite and adjacent are what I call relative terms. Relative means from your perspective. It's like left and right. Left and right are not a standard direction in this room. Right? You can't just put a sign on the wall and say, well, that's always left. No, it depends on which way you're facing. Right? For me, left and right is opposite for you, because we're facing different ways. That's how opposite and adjacent are. They're relative to something in the diagram. What they're always relative to is the angle that's marked, not the 90. Never relative to the 90. So pretend like you're standing at that angle. Opposite is always the side that is farthest away from you. This is opposite. It's the side that's completely across from you. If you were standing right here, pretend you were standing like right in the corner of that triangle, you could reach out and touch two of the sides. Well, the side that you can't reach is opposite. It's the one that's farthest away. Adjacent is the side that's right next to you. It's one of the sides that you could reach out and put your hand on if you were right in that corner. Now, you might say, well, there's two sides you can reach. Yes, but one of them already has a name, and that's hypotenuse. So adjacent is the side that's right next to you in a triangle that's not the hypotenuse. Right? And that's what adjacent means. Like if I said, the board is adjacent to me, adjacent means it's right next to me. It's adjacent. If I say something's opposite me, well, then that means it's across from me. It's in front of me. It's opposite. It's not right next to me. So now, if we take that same triangle, and let's change the perspective. So instead of pretend like you're standing in the lower right corner, let's pretend like now we're standing at the top. Now that's like standing and then turning a different way. Now left and right just changed. Opposite and adjacent just changed. This is still the hypotenuse. What side would be opposite now? Ethan?
The bottom one.
The bottom one. So remember, you're standing at theta. That's the point that was marked. Think of the two sides you could reach out and touch because they're right next to you. Opposite is the side you can't reach because it's farthest away. Adjacent is the side that's right next to you. That's not the hypotenuse. Okay, so opposite and adjacent can change depending on the angle that you're using as your perspective. You never use the 90 as your perspective. You have to use one of the small angles. All right. Any questions on that idea? Opposite and adjacent. So that's why I said in this first picture, when Ethan said something about opposite and adjacent, and I said you're missing something to know which one is which, it's because neither angle was marked. It'd be like walking into a room and somebody says to you, tell me which way is left in the room. Well, tell me which way you're facing first, and then I'll tell you which way is left, because I need to know how you're facing. Right? We didn't know which way we were facing in this triangle. Right? And that Greek letter, I think we mentioned it before, but that's the Greek letter theta. T-H-E-T-A. And it's theta. All right. So now I'm going to describe the 6 trig functions. I'm not going to use a coordinate like we did last week. We're going to describe them in terms of the words opposite, adjacent, and hypotenuse. Each trig function that we describe is a fraction. It's a fraction of 2 sides divided. So the sine of an angle is defined as the length of the side that's opposite the angle divided by the length of the hypotenuse. Divide those two, you get a decimal, that's your sine. If you want to know the cosine of an angle, that's the length of the side that's adjacent to you divided by the length of the hypotenuse. And tangent is the length of the opposite side divided by the length of the adjacent side. So one trick that you can use to try to remember them. Has anyone heard of the Sakatoa trick? So sine is opposite over hypotenuse. SOH. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And the last trig function, tangent, is opposite over adjacent. So if that helps, you can use that to remember. I asked one year if anybody remembered the trick for this, and somebody said Sacagawea. Not quite going to help you, but she did other things, but not Sacagawea. So those are your first three: sine, cosine, and tangent. Now, when we did these last week, does anyone remember what we did with each of these three to get the other three? Yeah.
We found the inverse.
Can you say, so what do you think the cosecant would be?
Hypotenuse over opposite.
Yes. So we're going to flip them. Okay. Which is a little different than inverse. So to find the cosecant, take your sine and flip it. Hypotenuse over opposite. To find the secant, take your cosine and flip it. To find the cotangent, take your tangent and flip it. Okay, and ADJ, that's just abbreviation for adjacent, and OPP is the abbreviation for opposite. And HYP is hypotenuse. I just ran out of space. Okay. Any questions on those 6 definitions? All right, so let's try an example that asks us to find the 6 trig functions of theta. Now, you could do some of them right now, but you're missing something to be able to do all 6. What am I missing? Yep.
Hypotenuse.
I'm sorry, maybe. Brian. Yeah, missing the hypotenuse. So the first thing you want to do is find the hypotenuse. Well, how can you find the hypotenuse if you know 2 of the sides already? Should I call you Brian? No, I'll call you.
The Pythagorean theorem.
Yeah, we're going to use the Pythagorean theorem. So if you want to just call that side C for now, let's set up the Pythagorean theorem. Mia, could you set up the Pythagorean theorem for me with this problem to solve for C?
Would it be 4 squared first or 3 squared?
You could do a 4 squared first.
Plus 3 squared plus C squared.
And what goes here?
C squared.
And what goes between them?
Additional squared.
Okay. Close. Anybody tell me what, we don't have anything to solve there. Because to solve it, we need 2 sides of an equation. Right now, we don't have an equation.
It should be 4 squared plus 3 squared equals C squared.
Yeah. So 4 squared plus 3 squared equals C squared. That's going to give me 25, which means the hypotenuse in this case is how much? 5. If the hypotenuse hadn't come out to a nice number, we could have gotten a square root. And remember, we talked about leaving square roots in the bottom of the fraction. If you get a square root, don't leave it in the bottom. Okay? But we don't have to worry about it this time. All right, let's do our trig functions. Okay, so Dylan, what would the sine be of theta? Well, they're all fractions.
Oh,
They all have to be fractions. What's the definition of sine?
Opposite over hypotenuse.
Yep. What's the opposite in this case?
4,
4 and the hypotenuse?
5.
And there's your sine. 4/5. Devin, how about my cosine?
It will be 3/5.
3/5. And Bridie, how about my tangent?
It would be 4/3.
4/3. In general, when you're doing trig functions like this, you don't have to find the decimals. We just leave it as a fraction. Don't leave square roots in the bottom. That'd be the only thing. All right, so we got those. Tyler, what am I going to do with each of those three to get the last three?
Me?
Yeah,
Don't we have to flip them?
flip them. All right, so very simple. So it's going to be 5/4, 5/3, 4/3. 3/4, sorry. Now, in that problem, just to point out what we didn't do, we didn't find the size of this angle. We found out 6 things about this angle. We know the sine of it, the cosine of it, the tangent of it. We know a bunch of things about it. But what we still don't know is theta. If we wanted to get theta and figure out the size, we'd have to get rid of the sine function. And what did we learn yesterday? Cancels out the sine function. Yep.
Inverse sine.
Inverse sine. So if you took the inverse sine of each side, you could figure out exactly what that angle is. This is the kind of problem we did yesterday. But today we're not doing anything else with that. Questions on that? All right, so getting into the last thing, complementary angles. Anybody remember what that means? You usually study it when you study supplementary, and people usually mix them up. Complementary means something. First of all, it applies to 2 angles because it's plural. So you need 2 angles to have complementary.
When 2 angles add up to 90 degrees.
2 angles that add up to 90 degrees. How come if you draw a right triangle, two acute angles, which I just labeled angle 1 and angle 2. Why will the 2 acute angles always be complementary? Yep. Yeah.
Because a triangle adds up to 180 and you subtract 90 because it's a right angle, and then you have to divide 90 between 2 angles
Yeah.
because the sides are equal.
So yeah, we got 2 angles here, and we don't know what they are, but we know we've already used up 90. So together, angle 1 and angle 2 have to add up to 90, or the triangle wouldn't add up to 180. All right, so I'm going to show you what we call in trig cofunctions. So one way to compare trig functions up is the way that we did it here. These are called reciprocal functions. Reciprocal means you flip one to get the other. So sine and cosecant are reciprocals. Cosine and secant are reciprocals. Tangent and cotangent are reciprocals. Flip one to get the other. Cofunction, very simply, is just when you take a trig function and you put the word co in front of it. So what function would you get if you put the word co in front of that? Yep. Cosine. So sine and cosine are what we call cofunctions. How about secant? What would be the cofunction of secant? Yeah. Cosecant. So when you take a trig function, put the word co in front of it, You get cosecant. How about the cofunction for tangent? What do you think we call that one? Cotangent. So these are what we call the cofunctions when we talk about this in trig. Sine, cosine, secant, cosecant, tangent, and cotangent. Any question on these pairs? That's it, that's all. Now, if you started with cosine, and somebody said, well, what's the cofunction of cosine? You don't put co in front of it again and say cocosine. It's kind of strange. You just say sine. So if it already has co in front of it, then you take the co away. Right? And that's the other. But those are the pairs. All right. So let's take a look at this triangle. And this is going to show us our last thing we're going to do. So I've drawn a triangle, and I've labeled the sides the way we usually would label them, just like in Pythagorean theorem, A, B, and C. And when we have an angle we don't know, we always use a Greek letter. And in this case, the Greek letters we're going to use are alpha and beta. It's a good habit to get into when you're doing a right triangle. Always put A opposite alpha and put B opposite beta. If you want to draw your triangle this way, that's fine. It's just once you put your sides in, put your angles in the right spot. A across from alpha, B across from beta. That's the same triangle. You switch the A and the B, that's fine. So then make sure you put the A across from alpha and the B across from beta. That's all. And C should always be the hypotenuse. All right, let's pick a pair. Let's pick these two. Let's do sine and cosine. So let's find the sine first. And let's do the angle down here, alpha. All right. Noah, can you remind us, what's the definition of sine?
Isn't it y value over x value?
If you were doing unit circle trig, it would be the y, just the y value. But how about on a right triangle? Yep.
Opposite over hypotenuse.
Opposite over hypotenuse. And how about, Kavani, what is the side that is opposite this angle?
The beta.
So it would be either A, B, or C.
Oh. B.
Which one did you say, B? So B would be opposite beta.
A.
Yeah, A. A is the one that's opposite from alpha. So opposite is A. And Haley said sine is opposite over hypotenuse. Justice, what's the hypotenuse?
C.
C. Alright. So when we do the sine of alpha, we get A divided by C. Now, instead of sine, let's do the cofunction. And instead of alpha, let's do the other angle. Let's do beta. So I'm doing two things. I switch the function to its cofunction. I'm just making up a new problem. So the way I did it is I switched the function and I switched the angle. All right, cosine. What's the definition of cosine? Okay, Caitlin?
Adjacent over hypotenuse.
Adjacent over hypotenuse. Now pretend like you're standing at beta. What side would be adjacent to you if you were standing at beta? Yep. A. Adjacent over, Caitlin said hypotenuse. What side is the hypotenuse? Justice?
C.
C. What do you notice about the about the sine of alpha and the cosine of beta?
They're the same.
They're the same. Alright. Let's try one more of those. Let's pick another pair. Tangent and cotangent. Let's do the tangent of one angle, and then let's do the cotangent of the other, and see what happens. So again, the pattern here is, this is tangent, that's cotangent, this is alpha, and beta is what we call the complement. Because when we said alpha and beta always add up to 90. So I picked one of the angles, and then I picked its complement. It's the other one that would add up with it to 90. All right, so tangent. Natalie, what's our definition for tangent?
Opposite over adjacent.
Okay. Opposite over adjacent. A over B. And how about, Gina, what's our definition for cotangent? Adjacent over opposite. So if you're standing at beta, adjacent is right next to you. Opposite is across from you. A over B again. So we got the same answer. And the whole key is this and that are cofunctions. This and that are complementary angles. Because that's what we said right here. The two angles that are labeled 1 and 2, or alpha, beta, whatever you want to label, they're always complementary. So as long as you have cofunctions and angles that are complementary, you'll get the same answer when you do that problem out. And that's called the complementary angle theorem. As long as you have cofunctions and you have angles that are complementary, the answer that you get when you do either problem is the same. So on the left, I have sine of 30 degrees. And using this theorem, I want to figure out something that it's the same as. So let's see what the theorem says. Find the cofunction, find the complement, and it will come out the same. So what's the cofunction of that? Yep, cosine. And what's the complement of that? 60. So if you type that in on your calculator, the sine of 30, sine of 30, cosine of 60, you get exactly the same thing. They're both 0.5. I didn't really care that they're 0.5. I wanted to show you that they're the same. From now on, I don't care what they come out to. I just care that they're the same. How about this one? The tangent of 15. Don't care what it is. I just want to know what is it the same as. So think of the cofunction, and then think of the complement of 15. Yep.
Would it be cotangent 30 degrees?
Cotangent of how much?
30 degrees?
So complementary means these have to add up to what?
Oh, 180. Wait, 90.
90.
So it'd be 75.
75. And how about the secant of 40? What would that be the same as? Again, don't care what it is, I just want to know what it's the same as. Yep.
Cosecant 50.
Cosecant 50. So, knowing that, we should be able to figure out this problem. Now, 15 and 75 are not angles that I have memorized off the top of my head. I don't know what the sine of 15 is. And I don't know the cosine of 75. But sine and cosine are what kind of functions? Yep. These are cofunctions. And 15 degrees and 75 degrees are what kind of angles? Complementary. So we have cofunctions of complementary angles. So what does that mean about this value compared to that value? Yep,
It means they're equal.
they're equal. We still don't know what they are, but we don't need to know what they are. We know that what's in the top and what's in the bottom are equal. So what are you going to get when you divide them? 1. Now if you change that 15 to a 16, that messes everything up. You can't do it. As long as you have cofunctions of complementary angles, you know you have two things that are equal. And when you divide two things that are equal, you always get 1. How about this one? The tangent of 12 minus the cotangent of 78. Yep. 0. Cofunctions. Complementary. That means this and this are equal. If you subtract two things that are equal, you always get 0. Now, if you add two things that are equal, do you always get the same thing? No. What happens if you add two things that are equal? What do you get in general? You get the thing doubled. Okay, whatever the thing you started with doubled. Same thing with multiplication. If you multiply two things that are equal, you don't always get the same thing. If you divide two things that are equal, yes, you do. Questions on that? Okay. So, homework for tonight on page 187. Those questions are all yes or no. Okay, that's the first part of what we did. And page 255, that's on opposite, adjacent, and hypotenuse stuff. Okay, 9 to 21, just the odds.
It was